name is Olena Kutsenko, and this is Apache Kafka Simply Explained. Today we are going to talk about an open source platform you undoubtedly heard of, unless of course you came here to listen more about Franz Kafka. Then I must disappoint you, because today we are going to talk about a distributed event streaming platform which exists already for over 10 years and became de facto standard for data streaming. It is widely used in the industry, but still somehow challenging to understand. That's why today our goal will be to look at this technology and its fundamental building blocks in simple terms. Doesn't mean that we will not dive deep, but we'll try to keep it simple. So what is our plan for today? We will start with a bit of a background story where the need for Apache Kafka is coming from. Then we will dive into some theoretical basic concepts and fundamental building blocks. And we will iterate the theoretical part with a bit of a practical exercises. I have prepared a GitHub repository with more detailed instructions how you can run those exercises and demos. So if you're good at multitasking, you can do it here and now, or also feel free to take it and do it later after the session. And finally, we will touch a couple of more advanced topics, and I will leave you with some ideas what you can do next if you are planning to work with Apache Kafka. And before we give a definition to Apache Kafka, what I wanted to do is to give you an example of a project where Apache Kafka makes a significant difference to the users and to the developers. And my ingenious project idea is based on the animation movie Zootopia, which you might have seen. And if you didn't see it, no worries, it's not really important. But if you had, then you will recognize some of our characters. Because today, you and me, we are going to build the first e-commerce product of Zootopia, and we will call it ShopiTopia. Like in any e-commerce project, we expect to have some kind of inventory of the products, where our fluffy customers can search for products, select what they need, what they want, place an order, pay, and wait for delivery. And this probably will be the minimum set of the features which we expect from this product. And maybe during the MVP stage, we would prefer to keep all our modules within some kind of monolith close to each other, where our front-end will communicate directly to our back-end modules for ordering, payment, and delivery, and where we have also some kind of storage with information about the customers and the products. And it all will be interconnected. And this might work at start, when we still have small amount of functionality, users, and products. But once we start scaling and growing, once we have more interest from our customers, we probably want to add some other cool things. For example, instead of just a simple web interface, we want to introduce also Android and iOS app. We want also to give a possibility to users to get notification from the system, recommendations to suggest them some other cool stuff they can buy based on their previous purchases, and the delivery tracking mechanism to follow the parcels which are coming to them. And if we continue adding these new modules into our monolith, very quickly the architecture and the information of this system will become a mess difficult to support and difficult to expand. And with the development team growing, no single individual will be able to keep up with the flow of information in this system. It probably will become as painful as untangling the cable headphones after they're in your pocket. Or maybe I'm the only person who is still using cable headphones. So at this point of time, we will need to have a tough conversation on how we are going to divide this monolith into a set of independent microservices with clear communication interfaces. What's even more crucial, our new architecture should allow us to be as close to real-time communication as it is possible, to rely on real-time events so that our customers don't have to wait till tomorrow to get meaningful recommendations based on the activity done yesterday. Because nowadays, everyone, including us in this room, expect immediate feedback on our actions. What would be also super cool if our new architecture would allow us to have some kind of real-time monitoring, reporting, and data processing. And admittedly, this is a lot to ask. Introducing such activity tracking into a system like this is an immensely high volume operation, and with the amount of users growing, products, and functionality, the complexity of the system and kind of communication paths will grow exponentially. However, luckily, Apache Kafka is designed to help exactly in these situations. Apache Kafka is great at untangling data flows and simplifying how we handle real-time data. So, keeping this in mind, let's now come back to the definition of Apache Kafka. And I know definitions are boring by default, but it's so important for us to be on the same page. So, what is Apache Kafka? It is an event streaming platform that is distributed, scalable, high throughput, low latency, and has a very big ecosystem. Or, simply put, it is a platform to handle transportation of messages across your multiple systems, across your microservices. Can be like in our example, some front-end services, some back-end stuff, but can be also a set of IoT devices. Maybe it is a teapot in your kitchen sending information about the water temperature to some back-end services. Apache Kafka is distributed, meaning that it relies on multiple servers with data replicated over multiple locations, so that if any of the servers crash, then we still have our data intact. And it is scalable, meaning that we can have as many of those servers as needed, and we can handle as many as millions of messages coming through our system on a daily basis with petabytes of data persistently stored over the disks. And what is cool about Apache Kafka is its community and a big ecosystem around it, including the client libraries for different languages, and we will see today one in action for Java, but also there are libraries for Node.js, for C#, and many others. And there is also a set of modules which we call connectors, which will help you to connect or integrate your existing services with Apache Kafka cluster. And so that you don't have to reinvent the wheel when you start working with Apache Kafka, but can rely on the work of other engineers who already run into similar challenges and solve those. And to understand how Apache Kafka works and how we can work with Apache Kafka effectively, we need to talk about Kafka's way of thinking about data. Kafka's approach is quite simple, but also quite clever. Instead of thinking of data in terms of static objects or final facts, final information stored on a table in a database, Apache Kafka describes and deals with data in terms of continuously incoming events. So let me explain. In our ShopiTopia, in our online shop, we have a set of products we sell. And those products we can describe in a table, in a database, with information about the availability, how many items we sold, and so on. And this would give us very valuable information. However, in case we want to answer some additional questions, to get some data about the sell trends, demand, peak search times, we cannot that easily deduct this information from the table unless we plan this in advance. Because anything which is stored in the database, in the table, is a compressed snapshot. It's kind of one-dimensional view, or we can think of it as a one point on an infinite timeline. So what if, instead, we will think about this data in terms of flowing events. So, some customer ordered a tie. Another customer searched for a donut. Then the previous customer, we dispatched the tie to the previous customer, and the second customer decided to order a donut. And so on, we have more events coming into our system. So this shows the whole life cycle of product purchase. And instead of seeing a single data point, we observe the change of state. We can replace the events from the start. We can move to a given point of time. We cannot change the events, they already happened, but we can kind of relive them again and again, calculating metrics and answering questions about products and sales. And in this way, those events will give us kind of 360 degree on our information, on our data. This type of architecture you might be actually familiar with. It is called event-driven architecture. And let's look how Apache Kafka works with the event-driven architecture. So we have Apache Kafka cluster, and I will put it here into the middle, and everything happens in the middle, it happens within the cluster. And on the left and on the right, we will see how other applications interact with Apache Kafka cluster. Apache Kafka coordinates data movements and takes care of incoming messages. It uses a push-pull mechanism to work with the messages. This means that on one side, we have structures which will create those messages and push into the cluster. And on the other side, we have structures which will pull those messages and read them. So those structures which push the messages are called producers, and these are applications you write. And those who pull the messages are consumers. You can have as many producers and as many consumers as you need. In our case, the producers can be connected to the front-end applications, observing user actions, packaging information, and sending it to the cluster. And the consumers can be connected to the notification service, recommendation engine, and the rest of the services. Reading or pulling messages one by one, reading and doing whatever you need to do to get the necessary stuff for those services. Producers and consumers are written or can be written in different languages, different platforms, completely not knowing about each other. In this way, we can separate our big monolith into a smaller independent microservices and have a communication through the Kafka cluster, because all of those producers and consumers, they know about Kafka cluster, they communicate with the Kafka cluster. It is possible that we decide to shut down some of the producers and add some new ones, and for consumers, it doesn't really make any difference. They will not even notice that something changed with the messages, they just continue reading the messages. And it's also possible that some of the consumers crash, so while it's being recovered, producers still continue working and sending the messages into the cluster, because what we store in the cluster is a permanent storage. So when consumer recovers, it can start where it left off. So there is no synchronization expected between producers and between consumers. They work at their own pace, at their own convenience. Now let's look what happens within the central area with the records. So historically, a set of homogeneous events, meaning events coming from some kind of source with similar content in those events, is called a topic. A topic is actually an abstract term. So let's say it's not how we store the data, but how we are thinking about the data, just to simplify our life. And topics are similar to tables in the database. So you can have as many topics as you need. For example, this one can contain events related to product ordering cycle. We can also have a topic with user registration events and conversion, or maybe a topic with application state, some errors, warnings, and any other health states which our application is producing. the data is continuously flowing into the topic. There is no breaks, no pauses. It's like water in the river. If our application continues working, we always have some users registering, some products being purchased. And the messages in the topic, they are ordered. Each message has a sequence number, and we call this number offset. And this number uniquely identifies position of a record within the sequence. Also, the messages are immutable. And this is kind of logical because think of it, someone bought a donut. You cannot really go into the past and change that event, unless of course you're Michael J. Fox and you have DeLorean, but otherwise you cannot. So if you don't like the donut, you can throw it away, but technically this is a new event. Also, when looking at the topics, you might think that they resemble queues. However, there is a twist. In Apache Kafka, unlike in many other queue systems, the consumed messages are not removed from the topic and not destroyed. So it's actually quite common that we will reuse the same messages, the same topic for different consumers, approaching data from different angles because, as we said, we have this 360 view on the information. So in our case, we can use the information about the product purchase for the recommendation engine, for the notification service, and so on. Cool, so we learned a bit about topics, and how about we create our own producer and our own consumer for to send the messages and pull the messages from the topic. So in the GitHub repository, I have more detailed steps, but overall there is a project, there are some dependencies which you can install. There is a configuration file with parameters which you need to fill in to connect to your Kafka cluster. And yes, for these exercises, you will need to have your Kafka cluster. Since Apache Kafka is an open source product, you can set up the cluster from the source code, or of course, if you don't want to do this, you can use one of the many available managed options. And because I work in Aiven, then I should mention how much love my colleagues put into Aiven for Apache Kafka, and you can use it as well. You don't really need to provide any credit card details or anything else for registration, and it will be, the free trial will be totally sufficient. In this demo, we are going to focus on a single topic. And what we are going to do, we have our Kafka cluster, and we want to send records with the help of a very simple producer, and then pull the data with the help of a very, very simple consumer. But before we start writing the code for pushing and pulling the messages, we need to configure our producers and our consumers so that they know where the Kafka cluster is located and how to work with it. So we need to connect to the cluster, and we have some properties which we need to set up. So the address of the Kafka cluster, as well as the serialization mechanism, so in which format the data will be transmitted. We also need to make sure that Kafka cluster can trust our producer and our consumer. And I'm using here SSL mechanism, and those properties are the same which are in configuration file, which we have seen a couple of minutes ago. So now that we have information about the connection to the server, we can move and create our own first producer. And this is actually quite simple. We are going to use the client library for Java, and we are going to create a producer object. Then we are going to generate some kind of a message. It can be a string, can be something else. I decided to have just a JSON object. And then we will package that object, that message, within the record, and we will send the record to the cluster. And this is for one simple object, but of course, for this demo, I wanted to imitate that we have a flow of events coming non-stop. So I covered this with a while true loop and 1 second of delay. I hope you will forgive me this simplicity. And the generate message method is just creates a JSON object with 3 properties: customer, product, and operation. And we have 2 operations here, either someone searched for a product or someone bought a product. So if we run the main method of our simple producer, we can see that we connect to the cluster and then we start sending small JSON objects to the cluster. So our topic in the cluster is slowly populated with the information. So it's time to create a consumer and to read those messages. Creating consumer is quite similar. Again, we will create a consumer object based on the client library. Then we will subscribe our consumer to the topic, to the same topic into which we right now started sending messages. And finally, we will pull the data. So I just log the information about the records. Of course, in the real systems, there will be something more complicated happening here. So, and we can start our consumer now. And again, we are connecting to the cluster using that SSL mechanism. And once we are connected, we will start receiving the messages or pulling the messages. This takes a bit of time. Pulling the messages and outputting the information about the content of the message. So in this way, we have a very simple producer and a very simple consumer. How about we will add two new concepts, brokers and partitions. I already mentioned that Kafka cluster relies on multiple servers. And in Kafka world, we call those servers brokers. Topics are supposed to be stored somehow on those servers, on those brokers. And yeah, we can think that if we send continuously objects and if we persistently store the data, Kafka topics will eventually grow to quite a big size. So we need to find an effective way to store that information across the brokers. And remember I mentioned that a topic is actually an abstract term. A topic is not a tangible physical thing stored on the servers as a whole. It's probably neither reasonable nor feasible to keep the topic as a single object on a single machine's memory. Because one day the size of the topic probably will outgrow the server's memory. So we need to find the way how we are going to do the replication horizontally and not vertically. And for this, we are dividing our topic into multiple chunks. And those chunks will be stored on multiple machines. And those chunks have names partitions. Partitions are technically logs of messages, and you might be familiar with the log structure, but if you're not, it's a very simple type of structure, append-only sequence of records ordered by time. So we always put to the tail of that document new messages. And those logs, or we will be calling them partitions, are stored across brokers. Partitions are independent, self-sufficient entities. They are responsible for their own offset, those sequence numbers. And this means that right now this cool, nice numbering across the partitions is actually wrong. It doesn't really work like this. Instead, we have independent offset numbering per partition. This means when I'm saying that the record with offset number 3, I need to specify of which partition, because it makes sense only within a single partition, that numbering. When I was saying that a producer pushes messages into a topic, what I meant that the producer pushes messages into a set of partitions, and the consumer pulls messages from the set of partitions. And behind the scenes, our producers and our consumers, they know how to work with a set of partitions. However, this includes a couple of challenges for us as well. And a spoiler alert, the challenges are related to the ordering of the messages. Because we want, most of the times, to keep the same ordering when we read the messages as those messages were sent by the producer. To understand the challenge, let's look how we are sending the set of messages into the topic. So our topic consists of 3 partitions. And we have this flow of events. And if we don't do anything, Apache Kafka will smartly try to separate or divide those records across partitions in some effective, some efficient way, focusing on just being fast and efficient. And then we would like to read those messages with the help of a consumer. And here is a challenge. Because our consumer also want to be fast and efficient, they might connect to a server which has partition 3 first and read messages from there and then just go around the servers with different partitions. We cannot predict the sequence of partitions, how our consumer will be reading. We can only predict the sequence, the ordering of messages within a single partition. And of course, for us, it's quite important that the ordering of messages when we read is correct. So if we have our customer ordering a product, we expect the customer first will put the product into the basket and then pay for it. If those messages are messed up, this is kind of useless for our system. So for keeping the messages, the ordering of the messages correct, we need to separate and divide them into the topics, into the partitions, in a way that all the messages from the same customer will get into the same partition. And then we will maintain the right ordering of the messages. And we can do this with the help of the keys. So every record, apart from the record body, the value of the record has a key. And the key plays a dramatic role in how we are distributing messages across partitions. Because all messages with the same key will get into the same partition. So again, if we have some kind of events related to the product purchased by some of our customers, then when we start dividing the records across partitions, then we can be sure that all the records, for example, related to the fox will get to partition number 0, for the piggy to partition number 2, for the bunny to partition, for the piggy to partition number 1, and for the bunny to partition number 2. And in this way, when we then start reading this information with the help of a consumer, we can rely on the ordering and know that the ordering is not messed up. But you don't have to believe me, we can look at the demo. So first, without any keys, I just wanted to iterate a bit on our consumer and add a couple of additional properties which we are going to output so that we see which partition, from which partition we are reading the messages and which offset those messages have. So if we run this new, more advanced consumer, and I'm not sure if you can follow, but you can kind of observe that there is no correlation from which partition, which messages in relation to which customers are coming. Right now it's all messed up. And I also created another consumer where I output only data in relation to a single customer, to Judy Hobbs. And we can see that right now, if we don't do anything extra, the messages related to the activity of Judy Hobbs will be coming from all possible partitions. And we have 3 partitions here in a topic. So this is problematic because we cannot be really sure that this is the same order as our producer was sending events into the topic. So what we are going to do, we are going to add the keys to fixes. And to add the fix, we're going to modify the producer and modify the place where we are packaging our message within the record. And now we are going to add the key to the record. So our record will be identified by the topic name, key, and then the message or the value of the record. And if we run this improved, so we are running this improved producer, and then the consumer reads from the topics, now we can see that all the messages, for example, related to activity of frou-frou coming from partition 0. And the Mayor Lionheart activity comes from partition 1. And also if we look at the filtered consumer, where we just have data related to the activity of Judy Hopps, we can see that all the information is coming from partition number 1. So in this situation, we can see that there is this single flow, so there is no confusion across partition, or there is no possibility for the ordering to be confused by the ordering of partitions. So this is how partitions works. And so we talked about topics, we talked about partitions. Let's make one step further and talk about replications. Replications are important because, of course, we don't want to lose accidentally any of our data, but we also know that stuff happens and servers break. Something can really go not how we planned, or maybe we need some maintenance window, so we need to have copies of our data, just in case. So let's come back to this slide where we were talking about how we are separating a single topic across multiple partitions. And dividing a big topic into digestible chunks gives us kind of a more straightforward or kind of even elegant possibility to replicate the data. To achieve this, to achieve the replication, each of the brokers will hold several partitions, not only one, but several. So now, in this picture, we have 2 copies of partitions per every broker. And if any of the brokers, like something happens, then we still can be sure that the data will be complete. And this is actually, since we have 2 copies of data, this is called replication factor of 2. Normally, the accepted practice is to use replication factor of 3, and you can imagine how this picture will look if we have 3 copies of our replicas across 3 copies of our partitions across the brokers. And replication is cool. However, it introduces some more questions. And the first one, once we have the replicated partitions, to which one we are writing data and from which one we are reading data? And the oversimplified answer is that we always write and always read from the leader replica. So there will be one leader replica and the rest of the replicas we call follower replicas. This involves some cool stuff like leader election and leader re-election when needed. So almost democracy, but not really. So this is how it works. Also, another question which you might have is what happens to the data which we send into the cluster if the leader replica crashes? Even assuming that the server will recover or there will be new replica elected, still takes some time. And as we said, producers never stop working. So are we fine with losing the data, or how are we going to fix this? And we actually have 3 different options for this, for 3 different use cases. The first one feels almost like cheating, because the first one is doing nothing. Maybe we are fine that we will lose some portion of our data. And this can be in situations where, for example, we have this tracking delivery service which observes the movement of the vehicles with the parcels. And those vehicles, on some regular intervals, they will send the location to the topic. And we might be fine with losing some of those locations because we can approximate the position of the vehicle based on the previous data points, and overall this is not mission critical information. We might prefer to sacrifice some data completeness for the sake of simplicity and performance. But of course, this is not the common case. Commonly, we do not want to lose any of the data. So what we can do, we can ask for acknowledgement for the confirmation that the message was received. So what happens? Producer will send the message to Kafka cluster, catch that message, and send a confirmation back that, great, I got your message. You can continue sending me new messages. And then producer can be sure that everything went fine and continue working. And this will have a bit of performance effect because, of course, we need to do an extra loop. However, for the sake of completeness of our data, it is totally worth it. However, there is one scenario, or there is a possibility that the data will be lost even in this case. And this can happen if a producer sends the data, the replica receives the data, and then suddenly crashes before having the opportunity to replicate the data to the follower replicas. So technically the producer will get the green light, but practically we lost the data. So there is one more option, even though this possibility is quite low. In case when we work with some medical records or some financial data, we probably want to be quite sure that we have completely all the data replicated. So another option would be to ask for confirmation